Bushur. Today I am going to give you a presentation on the cluster algebra. Cluster algebra. Aim of this course, aim of this lecture, cluster algebras and cluster algebras and related basic definitions with the examples and the second one, QR representation and a cluster algebras. QR representations and the cluster algebras. So first, introduction of cluster algebra. Cluster algebra were introduced by Fomin and Zelevinsky in 2000, motivated by the total positivity and listic canonical basis. Cluster algebras are a class of commutative rings. A cluster algebra, suppose a set, first we are collecting by using basic definition we will get set of cluster variables. So this set will generate an algebra. This algebra is called the cluster algebra. Cluster algebra constructed from initial seeds as follows. Suppose if you are mutating repeatedly, mutating your seeds, we will get finite or infinite QR. So infinite, we will get infinite QR. So and then if one can be obtained by mutating the other. So then first I will start with a QR. What is QR? So cluster algebra from QRs. Cluster algebras from QRs. So QR is a quadruple definition. What is QR? A QR Q. This is Q0, Q1, S comma T is a quadruple consisting of two sets. Consisting of two sets Q0, Q1 and two functions S and T. Consisting of two sets Q0 and Q1 and S comma T, two maps. This is mapping from Q1 into Q0, where Q0 is the set of all vertices, and Q1 is the set of all arrows or edges. So mostly S represent a source, T represent target. Suppose alpha is suppose alpha belongs to Q1 for any arrow. So S of alpha is a source and S of T for this S of alpha is source, T of alpha is target. So usually we are taking by a point A for S of alpha, B is point for T of alpha. This QR is A to B. Here A is T of alpha, B is A is S of alpha, B is T of alpha. So your QR is usually denoted by QR. Q is Q0, Q1, S comma T is usually denoted by Q is Q0 comma Q1 or more simply only Q. So Q represents Qer. So next example of Qers, I am giving simple examples. This were vertices, there are two vertices. This is example of Qers. This is simple. These are examples of Qers. Next, finite Qer. What is finite Qer? The set Q0 and Q1 are finite, then the Qer Q is finite. Yeah, Qer Q is said to be finite. Yeah, Qer Q is said to be finite if Q0 and Q1 are finite sets. If Q0 and Q1 are finite sets, there are finite number of vertices and a finite number of edges. These examples also finite Qers. Next, the underlying graph Q bar of a Qer is obtained from Q. Underlying graph Q bar, it is obtained from Q by forgetting the orientation of the arrows. By forgetting the orientation of the arrows The Qer Q is said to be connected. If Q bar is connected, the Qer Q is said to be connected. If your Q bar is connected graph, is a connected graph. So next one, path. We are studying our cluster algebra from Qers here. First I defined what is Qer and some examples, and what is finite Qer, underlying graph and a connected graph. These things we discussed. Now I'm going to tell what is path. A path, suppose these are vertices, this one is Qer and another one we are taking like that. Here this one is point A, this one is point B. A is S of, this is alpha 1, here alpha 2, here alpha 3, this is alpha 4. So our A is, so S of alpha, S of alpha 1, source of alpha 1 is A, and T of alpha 1 maybe this is T of alpha 1, this vertex is T of alpha 1, this vertex is T of alpha 2, this vertex is T of alpha 3. So T of alpha 1 it should be equal to S of alpha 2. T of alpha 2 it should be T of alpha 2 it should be equal to S of alpha 3. So T of alpha 3 it should be equal to B. So if it satisfies with this condition, it will form a path. This is path. Next, Q mutation. Next definition, Q mutation. So what is Q mutation? Let first here we are taking finite Q without loops or two cycles. Let Q be a finite Q. That means Q0 and Q1 are finite sets. Finite Q and without loops or two cycles. Let K be a vertex of Q. Let K be a vertex of Q. That is K belongs to, that means what? That is K belongs to Q0. Q0 is the set of all vertices. That's why K belongs to Q0. We define mutated Q. Mu K of Q. Mutated Q mu K of Q as follows. So it has the same set of vertices and a set of arrows defined as follows. Here it has the same set of vertices as Q. That means as Q0. It has the same set of vertices as Q0, and its sets of arrows is obtained by the following procedure. First one, we have to consider for each subQer of Q. For each subQer, first one for each subQer I into j into k is a subQer of Q. We add a new arrow. So I to k. That is, suppose we have a subQer I into j into k, like that. We have to make I into k. This is first one, and the second one, reverse all arrows. Reverse all arrows with source and target. Which is related to our k, mutating vertices k. Reverse all arrows with a source and target which is related to k. And the third one, remove the arrows. Remove the arrows in a maximal set of pairwise disjoint two cycles. We have to remove the arrows in a maximal set of pairwise disjoint two cycles. These are procedure for Q mutations. And examples, I will give now a few examples. first one. So I am giving a simple example, this one 1 to 2, here this is 1, 2, 2 to 3, this is one QR. So mutating of to mu2, so mutating this one with respect to 2. So first this is 1 to 2, 2 to 3 here. So that's why I want to make one arrow from 1 to 3. So I want to make one arrow, this is 2, here 1, here 3. I want to make one arrow 1 to 3 because we have one arrow 1 to 2 and another arrow 2 to 3. That's why we are making 1 to 3 from the first condition. And the second one, reverse all arrows. So we have to reverse this one. Here also we have to reverse. This is mu2. So again, if you are mutating this one, we will get first one. We will get first one. This is actually involution. This is actually involution. For all QRs, it will satisfy involution. Second one, second example. This is 1, 2, or sorry, 1, 2, 3, 4. Here one arrow, this is one arrow, here one arrow, this one also one arrow. So now mu1, we can take, we are taking mu1. Our mu1 is here 1, here 2, here 3, this place 4. So here consider mu1, 4 to 1 one arrow, 1 to 2 another arrow. So we have to make one arrow from 4 to 2. We have to make one arrow from 4 to 2 and reverse the other arrows. Other arrows means which is related to 1. So here we have to reverse the arrows. This is 1 to 4 1 and 2 to 1. All other arrows are same. All others are same. And here this is 4. So like that we have to mutate. So again, if you are taking mu1 from this diagram, we will get this one. You can verify this. That means this is if and only if. Another example. So another example, third one. So if you are seeing more example, clearly we will understand this one. That's what I am giving more examples. Here this is 1, 2, here it is 3. This place one arrow, here two arrows. Now we are taking mu2. So mu2 is you can see. This one 3 to 2, 2 to 1 is coming. That's what we have to make. So 3 to 2, 2 to 1 is coming. So we have to make 3 to 1. 3 to 1 here 2, this place 1, here 3. Already we have two arrows here. 3 to 2 one arrow, 2 to 1 one arrow. So that's why we are making 3 to 1 from the first condition. From the first condition here cyclic it will form. That's why we have to remove this. We have to remove this cyclic. We have to remove this. We have to remove this one and reverse other arrows which is related to mu. Here we have to reverse the arrow 2 to 3 and 1 to 2. 1 to 2. This is the mu2. So again we can take mu2 from this diagram. We will get this one. This is if and only if. Your exercise. First your exercise. here 5, here 3 arrows, this 4. This is exercise problem. You can verify this. Fourth one, x1, x2, x3 here, this place x4, x5, x6, so now we are taking mu2. So mu2 is, so this is x2, here it is x2, here x3, here x1, x4, x5, x6. Mu2 is here you can see x1 to x2, x2 to x5. We have to make one arrow from x1 to x5. We have to remove the cycle. Here 2 arrows are going. So 2 arrows are going. We have to make 2 arrows from x1 to x5. x1 to x5. Once one cyclic form, we have to remove this. We will get only one arrow. This place x1 to x5. And others reverse the arrow. We have to reverse it here. This place also x3 to x2, x2 to x5, x3 to x5. We have to make one arrow. This place also we have to reverse the arrow. Here we have to keep the same. This is mu2 from this diagram to that one. Again you have to take mu2 from this diagram. We will get same one. So lemma, our lemma is mutation is an involution. Mutation is an involution. That is mu k square of q. Mu k square of q. This is what mu composition of mu k of q is. We will get the same q. So if it is satisfied with this condition, that means it is involution. So this is from this side we are taking mu2. Again we are taking mu2 from there. It will satisfy the involution condition. This is involution. You can verify all diagrams. Your exercise. Verify involution from the above examples. Verify involution from the above examples. Next one, definition labeled seeds. What is labeled seed? Labeled seed. Choose m greater than or equal to n. Choose m greater than or equal to n positive integers. Let f be an ambient field. Let f be an ambient field. Ambient field of rational functions functions in n independent variables. In n independent variables. N independent variables over the q. This is x n plus 1 to xm. X n plus 1 to xm. A labeled seed in F. a labeled seed in ambient field F is a pair x comma q x comma q where first one x is x1 to xm forms a free generating set for f and the second one q is a qer on vertices 1 to n plus 1 to m whose vertices 1 to n are called mutable. Here 1 to n are called mutable, n plus 1 to m are called frozen. Whose vertices 1 to n are called mutable and whose vertices n plus 1 to m are called frozen. So we refer to X as the labeled extended cluster of a labeled seed. So we refer to X as the extended cluster as the labeled extended cluster of a labeled seed x comma q. So in this definition we are choosing m greater than or equal to n positive integers. Let f be an ambient field of rational functions in n independent variables over q. Our q is q of n plus 1 to qm. A labeled seed in f, we are taking a pair x comma q where x forms a free generating set for f and q is a qer on vertices 1 to m, 1 to n, n plus 1 to m. Our 1 to n are called mutable and whose vertices n plus 1 to m are called frozen. We refer to X as the extended cluster of a labeled seed. The variables are x1 xn are called cluster variables and the variable xn plus 1 to xm and the variable c, we are taking the set c x plus 1 to xm are called frozen variables or coefficient variables Generally we are studying our cluster algebra with coefficient variables and without coefficient variables. Next, seed mutation. What is seed mutation? I am going to give the definition for seed mutation. So from our labeled seed, we are going to get our cluster variables and frozen variables, that is coefficient variables. We are studying our cluster algebra with coefficient variable and without coefficient variables. Now what is seed mutation? Let K be a mutable vertex in Q. Let K be a mutable vertex in K be a mutable vertex in Q, and let xk be the corresponding cluster variable, and let xk be the corresponding cluster variable, then the seed mutation mu k. So our mu k is which is mapping from Q into Q dash, that is pair Q comma x into Q dash comma x is defined by Q dash is mu k of Q. Our Q dash is mu k of Q, and x dash is x union the set x k dash without the set x k. In seed mutation, we are taking k be a mutable vertex in the Q over Q, and let xk be the corresponding cluster variable. Then the seed mutation is defined by mu k. Mu k is mapping from Q into Q dash. Our Q dash is mu k of Q, and x dash is x union set of all x k dash minus xk. Where x k dash is direct the product of k to j xj plus direct product j to k, here also xj, here also xj. This relation is called the exchange relation. This is an exchange relation. This is the exchange relation. So with these things we are defining our seed mutation. So remark, mutation is also involution. Remark, mutation, here seed mutation also involution. Mutation is an involution. So our example, here we are taking the diagram. So I am going to write it here. For example, here x1, x2, x3, x4, x6, here 2 arrows, this place x3 to x2 1 arrow, x2 to x5 1 arrow, x5 to x1 is 1 arrow, here 1 arrow, x5 to x6 and x6 to x3. Now we are taking mu2. So what is mu2? From seed mutation we are going to get this. So mu2 of this one, same thing, first here same thing x1, but mu2 x2 we have to change it. The variable we are going to change this. Here x1 x3 these are same, x4 x5 x6 are same, but the variable x2 we are going to get new x2, that is x2 dash. X2 dash is multiply, here 2 arrows is coming, that's why we have to take x1 squared, multiply of x1 squared into x3 plus x5 divided by x2. This is new x2. So in this way we have to change your variable. This is involution from the remark, this is involution, you can verify reverse one. So also we have to do same things from your arrows. In your arrows we have to do same things. Here same diagram, previous diagram. Directly I will draw this. This is reverse one, here reverse. This place also reverse. So if you are taking mu2, the diagram you can get this one. This is involution because. So next another example. Example 2. Let Q be the quiver on two vertices. Let Q be the quiver on two vertices 1 and 2 with a single arrow from 1 to 2, that means x1 to x2, x1 to x2, 1 to 2. Let x1 comma x2 comma q be on initial seed, initial seed. We can perform seed mutations in type A2. A2 is the Dynkin diagram, I will tell you later. We can perform seed mutations. In type A2. So I am taking first this variable x1 to x2, mu1. I am taking mu1 here, mu1 here. We have to for first variable 1 plus x2 divided by x1. Suppose there is no so in your exchange relation, suppose first one is empty, that means we have to take 1. For finding new x1 dash we are using this condition, 1 plus x2 divided by x1, which is going to x2 is same. This is mu1, again mu2, this is a new x1 and x2. Mu2 is, we have to reverse the arrow, this place we have to reverse the arrow, here also we have to reverse the arrow. We have to keep x1 dash, new x1 dash same, 1 plus x2 divided by x1. We needed to find a new x2, that means 1 plus x1 divided by x2. 1 plus x1 divided by x2 means here 1 plus x1, here x1 is 1 plus x2 divided by x1, 1 plus x2 divided by x1 divided by x2. For finding x2 we have to use this 1 plus x1 divided by x2. By using this we will find 1 plus x1 plus x2 divided by x1 x2. This is new x2 here. In this skewer we are writing new x2, 1 plus x1 plus x2 divided by x1 x2. Again we are mutating this, we are taking mu1. Our mu1 is, we have to reverse the arrow, you have to keep x2 same, 1 plus x1 plus x2 divided by x1 x2. But this place you needed to find a new variable, 1 plus x2 divided by x1, that means 1 plus new x2 is 1 plus x1 plus x2 divided by x1 x2 whole divided by x1. Your x1 is 1 plus x2 divided by x1. If you are simplifying this, 1 plus x1 plus x2 plus x1 x2 divided by x1 x2, 1 plus x2 divided by x1. Just you can remove this. If you are simplifying this, we will get 1 plus x1 divided by x2. So this variable is 1 plus x1 divided by x2. Again you have to mutate this. This is mu1. Again you have to take mu2. Again we have to take mu2. mu2, that means first reverse the arrow here. Here this place we have to keep the same variable, 1 plus x1 divided by x2. So this place needed to find 1 plus x1 divided by x2. 1 plus x1 means this new x1, 1 plus x1 by x2 divided by x2. x2 means this new 1 plus x1 plus x2 divided by x1 x2. We are simplifying this. You have to cancel. Okay, we will get x1. So this new variable is x1. So first we are taking mu2 and mu1, mu2, mu1, mu2. Again we have to do mu1. We have to do mu1. This is mu1. Again we have to reverse the arrow. This is same variable, 1 plus x1 divided by x2. This place is x1. You have to keep it this same. For here you have to find it 1 plus x2 divided by x1. Our x2 is x1. 1 plus x2 for x2 equal to x1 divided by 1 plus x1 divided by x2. You have to cancel your 1 plus x1. We will get x2. So you can see we are getting same arrow. This is repetition. We have to stop this. You have to see this arrow and this one. You have to this arrow and this one. We are getting same one. This is repetition. That's why we are stopping here. Now we can write your cluster variables. Now from this we can write your cluster variables. Our cluster variables are, cluster variables are this is x1 comma x2 initial seed, initial variable, and a new one 1 plus x2 divided by x1 from these things, 1 plus x2 divided by x1 comma 1 plus x1 plus x2 divided by x1 x2, and one more variable 1 plus x1 divided by x2. These are your cluster variables. This set, it will generating an algebra. That algebra is called the cluster algebra. This is a generating set. These are cluster variables. From this set we can, from this set we will get an algebra. AQ is a cluster algebra generated by A. Generated by A. So here we have two variables. Suppose another in another example, suppose we have only one variable x. How to find your variables, cluster variables? So x for x1 is empty, x2 is empty. That's why I am taking 1 plus 1 divided by x, 2 by x, x comma 2x inverse. These are cluster variables. It is generating cluster algebra. It is generating a cluster algebra. Next example. Next example, here we are taking 1 to 2, 2 to 3. So how to find this? How to find this? First mu1, mu2, mu3, you have to take these things. Mu2 is, so from this one we are finding mu2, we will get 1 to 2. So we are getting like that. This is your mu2. For mu1, so from this we are finding our variables. Here mu1 is, we are getting these variables 1 plus x2 divided by x1 comma x2 x3 is same procedure, but we have to do this one. So for finding mu3, this is mu3. So it is mu1, it is coming from there. This is mu2. From mu2 we have to find the variable x1 comma x1 plus x3 divided by x2 x3. This is your mu2. For mu3 we are getting x1 comma x2 1 plus x2 divided by x3. So we have to do like that. So we have to do like that. Again from this we have to take mu1, mu2 and mu3. So each and every set we have to do this process. We find a total 9 cluster variables. In this example we will find 3 initial variables and 6 new variables. This total 9 cluster variables. We will have 9 cluster variables. This is one more example. You can finish this. This is the exercise problem. This is your exercise problem. You can finish it yourself. Next one. So definition for, now I am giving definition for cluster algebra. Fomin and Zelevinsky 2002 they gave general definition for cluster algebra. It is given by Fomin and Zelevinsky. Zelevinsky 2002. The cluster algebra AQ, the cluster algebra AQ is the set of xn plus 1 xm subalgebra of the ambient field F, of the ambient field F. Your AQ is a subalgebra of F generated by all the cluster variables. Generated by all the cluster variables. All the cluster variables. So your example, this is your example. I am giving the example from your previous one. The cluster algebra AQ is the subring F is C of x1 comma x2 generated by all cluster variables. Here ambient field F we are taking C of x1 comma x2. For x1 and x2 we are getting the cluster variables A. It is generating set. We will get cluster algebra AQ. The generating set x1. Already we found this from example 2. This is from example 2 x1 x2 1 plus x2 divided by x1 1 plus x1 plus x2 divided by x1 x2 comma 1 plus x1 divided by x2. This is example for cluster algebra. If you want to find more examples, just you can search the website of Bernard Keller and other people. You can find many examples. But here I am giving only one example. So remark, every cluster our remark. So remark first one, every cluster variable is a Laurent polynomial. Every cluster variable is a Laurent polynomial. Polynomial in x comma x1. Here we are taking only two variables. So in x1 comma x2. In your initial clusters, we are initial clusters. Every cluster variable is a Laurent polynomial. Second one, each Laurent polynomial has positive coefficients. Each Laurent polynomial has positive coefficient. Third one, there are finitely many cluster variables. Here in this example I am telling from this example every cluster variable is in general case also like that, but from this example I am giving this remark. Every cluster variable is a Laurent polynomial. Each Laurent polynomial has positive coefficients. Here in this example there are finitely many cluster variables. So next one, fundamental results. Next is some fundamental results. Let A be an arbitrary cluster algebra, that is AQ. Let A equal to AQ be an arbitrary cluster algebra arbitrary cluster algebra with the initial seed. With the initial seed q comma x. So Laurent phenomenon. What is saying Laurent phenomenon? Laurent phenomenon. So Fomin plus Zelevinsky. Fomin plus Zelevinsky giving Laurent phenomenon. Every cluster variable is a Laurent polynomial, is a Laurent polynomial in the variable from x, in the variables from x. The initial these are initial cluster variables. The only initial cluster variables. Next one, positivity theorem. Positivity theorem. Each such Laurent polynomial has positive coefficients. Positivity theorem. They are giving positivity theorem. Each such a Laurent polynomial, has positive coefficients, positive coefficients. Next, finite type classification. Finite type classifications. Finite type classification. We say A has finite type. We say A has finite type. A has finite type if there are only finitely many cluster variables. If there are only finitely many cluster variables. The finite type cluster algebras are classified by Dynkin diagrams. The finite type cluster algebras classified by Dynkin diagrams. Dynkin diagrams. So what is Dynkin diagram? So I will give the Dynkin diagrams here. your Dynkin diagrams. Dynkin diagrams. So your AN is, so AN is 1 to 2, okay, 1 to 2, 1 to 2 to 3 n, at least here for every n greater than or equal to 1 for defining AN, and DN is 1 to 2, 2 to 3, here n, this n minus 1, here your n should be greater than or equal to 4 for defining Dn, and E6, for E6 this is your E6, so E7 this is your E7, and E8 also we have to take like that. E8 is this is your E8. These are your Dynkin diagrams. So next I would like to show how to mutate in Java app. So just we have to go to Keller web page, Bernard Keller web page, and from search this one English version and come down. So here useful links. There are few useful links. Just we have to click this one, QR mutations in JavaScript and Java. So you can download your Java. Also you can do it in your system. Otherwise directly in online you can do this one. So here QR mutation JavaScript it is there. So I am going to show this. So new QR, this is for 4. I'm changing 2. Sorry. This is for 2. If you are mutating 1, you will get this diagram, mutation of 1, and again you are mutating 1, you will get same diagram, that is involution. If you are mutating 2, you will get this one. Again if you are mutating 2, you will get the same diagram. You can mutate 3. So you have to do like that. And one more new QR, I would like to change this. Only one variable. It is coming like that, only one. And new QR. So 2, this is 2, and for 3, this is 3 1. You can mutate this one, mutation 2, mutating 3, mutating 5, 3 4. These are there's finite QRs, finite variables. This is finite QR. Your live QR is this live QR. So live QR randomly. So randomly, okay. 4. I'm choosing 4. This is QR4, new QR. I'm going to new QR. This is 4, mutating 8. So you are okay. Sorry. Repeat random. This is your repeat random. Your live QR. This is live QR. If you are choosing a random 5, if you are choosing 5. Sorry, 5. So it is coming like that. Read number no needed. Okay, mutating, this is 6. So now repeated random. Repeatedly we are doing this one. It is coming like that. You can do like that. So this is it is going like that, it is infinity. This is not a finite QoR. So you will use this app in Keller web page, you can do this. Otherwise you can download your Java and do it in your system. Yes, thank you. So again I come back to our lecture. So now I am going to start QoR representation and cluster algebras. QoR representation and QoR representations and cluster algebras. So aim of this, my aim, by comparing Fomin and Zelevinsky bijection and Gabriel's theorem, we get the cluster variable xv. By combining our aim, by combining Fomin and Zelevinsky Zelevinsky's bijection and Gabriel's theorem. So we get the cluster variable. xv. xv is cc of v. xv is cc of v from the indecomposable representation. From the indecomposable representation. Here what is cc of v? cc of v is Caldero-Chapouton of v. Caldero-Chapouton of v. I will define this later. This is cluster variable. This is my aim. And here I would like to start with the basic definition. Here, what is finite QoR? Already I told what is a finite QoR. Now I am going to give the definition for representations. Definition of representation. Representation of the QoR. Let a Q be a finite QoR. Let a Q be a finite QoR. Let a Q be a finite QoR. Let a and a K linear representation. A K linear representation, or more briefly representation, representation V of Q. V of Q is defined by the following data. Following data. A first one, A is a finite dimensional K vector space. A finite dimensional K vector space V alpha for each alpha, for each vertex, for each alpha belongs to Q naught. And the second one B, a linear map V alpha, here V is a sequence of V alpha, and a linear map V alpha is mapping from Vi into Vj, for every alpha is mapping from I to j, for every alpha is mapping from I to j. So your V consisting sequence V alpha and sequence of sequence V, consisting of sequence V alpha. So your example, first one, consider a finite QR. Consider a finite QR without oriented cycles. First one, consider a finite QR without oriented cycles. That means it will not form is that is this is example for oriented cycle. 1 2 3 1 2 2 1 arrow. Suppose 2 to 3 is going 1 2 3 1 arrow. This is alpha, beta, gamma. So we cannot make 3 to 1 because gamma is going from 1 to 3. If you are coming 3 to 1, that one is not oriented. It is oriented cycles. This is not oriented cycle. This is example for not oriented cycle. So here from this we are making the representation. A representation of Q is a diagram. Your so first I am taking V1 to V2. Your alpha is mapping from 1 to 2. So V alpha is mapping from V1 to V2, and V2 to V3 is V beta, and V1 to V3 is V gamma. It is not necessarily a commutative. Next, second example, example 2. Suppose Q, your QR is 1 to 2 alpha. So what is the representation of Q? This is simple example. Representation of Q is V1 to V2. Your V alpha is mapping from V1 to V2. Next, Morbism of representation. If you are telling about Morbism of representation, then we can define our category of representations. Representation category. So next one, Morbism of representations. Morbism of representation is Morbism of diagrams. Morbism of representation is Morbism of representation is Morbism of diagrams. Let M is our M. We are taking, let M equal to MA pi alpha, and M dash is MA dash pi alpha dash, B2 representations, B2 representations, B2 representations, representations of Q. So a morbism of representation F is mapping from M to M dash, that is sequence F alpha. Sequence actually F alpha is mapping from MA to MA dash. A morbism of representations F is mapping from M into M dash is a family, F is F alpha, the alpha belongs to Q naught of K linear maps, F alpha is mapping from MA to MA dash. F alpha is mapping from MA to MA dash. So your A belongs to, actually your A belongs to Q naught. This is sequence A belongs to Q naught, that are compatible with the structure maps, that are compatible with the structure map, compatible with the structure maps pi alpha, that is for each arrow, that is for each arrow alpha is mapping from A to B. We have pi alpha dash, F alpha is FB pi alpha, that is the following diagram is commutative. Compatible means for each arrow alpha is mapping from A to B, we have pi dash alpha F alpha equal to FB pi alpha, that is the following diagram is commutative. MA into MP, this is MA into MP, pi alpha is mapping from MA into MP, MA dash into MB dash, this is pi alpha dash is mapping from MA dash to MB dash. Your F alpha is mapping from MA to MA dash, FB is mapping from MB to MB dash. This is commutative. And next so let F is, next we are telling about composition of morbism. So let F is mapping from M into M dash and G is mapping from M dash to M double dash, B2 morbisms, B2 morbisms of representation of Q, morbisms of representations of Q where F is sequence F alpha, or FA, whatever FA, we can take FA, A belongs to Q naught, and G is sequence of GA, A belongs to Q naught. Their composition is defined by the formula. Their composition so next their compositions defined by the defined by the family GF. Composition of G and F is GF is family of GAFA such that A belongs to Q naught. Like that we are defining. Then GF is easily seen to be a morphism from M to M double dash. Then GF is easily seen to be a morphism from M to M double dash. We have thus defined a, from this argument we can define the category of K linear representations. So here we are defining morphism of representations. This one is composition. Their composition defined by like that. So from this argument we have thus defined a category of K linear representation. Notationally we are taking representation of Q of K linear representations of Q. So we denote by, so small REP, this is we denote by REP of Q is a full subcategory of, it is a full subcategory of REP of Q consisting of the finite dimensional representations. Your small REP, it is consisting the finite dimensional representations of the finite dimensional representations. Okay. Next one example. For example, so here we have defined a category of K linear representations of Q. Small REP of Q is means it is a full subcategory of the subcategory of REP of Q. So full subcategory of this one, that is it is finite dimensional representations. So your example, let a Q be the Kronecker Qer. Let a Q be the Kronecker Qer. Sorry, this error like here 1 to 2. So a representation V of Q is a representation V of Q is given by K squared into K. This map is 1 0, here it is 0 1. So another representation V dash, this is one representation V, another representation V dash is given by another representation V dash is given by K square into K square. Here this is 2 by 2 matrix, here 0 1 0 0 1, here also K squared, this place 0 0 1 0. So both are finite dimensional, here both are finite dimensional So we have a morbism. Now we have a morbism V to V dash. Our V is defined like that, V dash is defined like that. These are finite, both are finite dimensional. Both are finite dimensional. We have a morbism V to V dash is, we have a morbism V to V dash is defined by here it is this is k square, here it is k, here k square into k square. This place here match is 1 0 0 1. This place matches is 0 0 1 0. So this one is 1 0. Here it is 0 1. So now we have to make the map from k square to k square. Here it is again 1 0 0 1 here. So from this map k to k square, here 1 0. So this is from this from this, indeed it is readily verified that indeed it is readily readily verified that 1 0 0 1 composition of this one, this composition is equivalent to this one 1 0 0 1 1 0. So composition of this one is equal to composition of this one, and so from this diagram we are writing this, and 1 0 0 1 0 1 is 0 0 1 0 1 0. So composition of these two equal to composition of this one. Here also composition of these two equal to composition of these two. So next lemma. Let Q be a finite QR. Let Q be a finite QR. Then representation, the category, two categories representation, K of Q and K of Q are abelian K categories, are abelian. These two are abelian K categories. Abelian K categories. Next lemma. From morbisms and composition, first we are defining category of representations and full subcategory of full subcategory, and these two are abelian categories. From this lemma we are getting these two categories are abelian categories. So next lemma. A morbism F is mapping from V to W, V into W of this category, is an isomorphism, if and only if its components is its components Fi are invertible. Fi are invertible for all vertices I of Q naught. So Fi are invertible for all vertices I of Q naught. That means these two, this map is an isomorphism. This is if and only if. So example for this lemma. Example, let Q be the Qer. Let Q be the Qer 1 to 2 alpha is your arrow, and corresponding representation V is mapping from, your corresponding representation V alpha is mapping from V into V1 to V2. V alpha is mapping from V1 to V2, the representation of Q. V is here, this V is a representation of Q. Next, by choosing basis in the spaces, V1 and V2, we find an isomorphism of representations. Isomorphism of representation. V alpha is mapping from V1 to V2. V1 to V2 is V alpha. This is K to V1, and A is mapping from K to K power P. This is K power P to V2, where we denote A the multiplication by A the multiplication by P cross N matrix A. We denote A the multiplication map by the P cross N matrix A. So we know that we have PAQ. So your PAQ is here, where I are 0 0 0. R is rank of the matrix. For invertible matrices, P and Q are invertible matrices. For invertible matrices, P and Q are invertible matrices. P and Q, where R is the rank of A. Where R is the rank of A. Okay. So let us denote the right hand side by by direct sum of IR and 0. Then we have an isomorphism of representations. Then we have on isomorphisms of representations. Isomorphism of representations. Here k power n into k power p. Here k power n again k power p. This is q. Here it is P inverse. This map is actually direct sum of IR and 0. We have an isomorphism of representation. We thus obtain a normal form for the representation of this QR. We thus obtain a normal form for the representation of this QR. We thus obtain a normal form for this representation of Q. Now the category is in fact an abelian. Now the category of Q is in fact an abelian category. So its direct sums, kernels, co-kernels are computed component weights. Its kernels and co-kernels computed by component weights. Its direct sums, kernels, co-kernels and co-kernels are computed component wise. Thus if V and W are two representations then the direct sum V and W, direct sum of V and W, we are taking like that, by V plus W is the representation is given by V plus W I. Here we are taking I belongs to Q naught for any vertices and we have to take for any arrows or wedges. Direct sum of V plus direct sum of V and W over I. This is direct sum of Vi and Wi for every I belongs to Q naught, and direct sum of V plus W alpha here for any alpha belongs to Q1. So this is V alpha, direct sum of V alpha and W alpha for every alpha belongs to Q1. So its direct sums, kernels and co-kernels are computed by component weights, and thus if V and W are two representations, then we can define like that. Direct sum of V and W we can take like that. So example, fix a representation your V is actually V1 to V2. This is V alpha is mapping from V1 to V2 of your alpha is mapping from 1 to 2. 1 to 2. So V1 here, V2 here, your V alpha is mapped. So this is actually your K power P here, and this one K power Q. Here is I R 0 0 2 by 2 matrix. So actually this is isomorphic to this one. Here also this is isomorphic to this one. So here V1 into V dash into V into V dash. So R on the rank of this one, this matrix. So V dash is isomorphic to, actually your V dash is isomorphic to V dash is isomorphic to A to K or direct sum of this A into 0 for P minus R. So 0 into K over Q minus R. So your V dash is isomorphic to this one. The kernel of a morphism of representation, the kernel of a morphism of representations, F is mapping from B into W is given by kernel of F I is kernel of F I. It is mapping from Vi into Wi. So endowed with the maps, endowed with the maps induced by the V alpha, and similarly for the co-kernels. So your V dash is isomorphic to this one, the kernel of a morphism of representation. We are defining like that, we are taking like that. So this is endowed with the maps induced by the V alpha, and similarly we can define our co-kernels. So next definition, sub-representation. Sub-representations. Let V be a representation. A sub-representation V dash, which is a subset of E, a sub-representation, V dash which is contained in V, is given by a family of subspaces, subspaces, a family of subspaces Vi dash is actually which is contained in Vi. Sequence Vi is a family of the representation V. Sequence Vi dash is a family of a representation of V dash. When V dash is a sub-representation of V. Actually, it is given by family of subspaces Vi dash which is contained in Vi for every I which is belongs to Q naught. This belongs to Q naught such that it will satisfy this condition V alpha of Vi dash which is contained in Vj dash for every alpha which is mapping from I to J. This is the definition for the sub representation. Next definition, simple representation. That means it has for simple representation it has no proper sub representation of V. It has only V and 0. A representation V is simple. A representation V is simple. V is simple provided there is no proper sub representation. There is no proper sub representation. There is no proper sub representation of V. So that is 0 and V are only 0 and V are only sub representation of V. Sub representations of V. So next one, a representation of V is indecomposable. A representation of V is indecomposable. If V is isomorphic to direct sum of U and W which is not equal to 0. For every which is not equal to 0 for every U comma V. Sorry, indecomposable. V is indecomposable if direct sum of U plus V equal to 0 for all U comma V, then this implies that U equal to 0 or W equal to 0. So equivalently a representation is indecomposable. Equivalent condition, it has exactly two direct factors. If it has exactly two direct factors, that is it is a indecomposable. A representation V is indecomposable. A representation V is indecomposable if it has exactly two direct factors. So example for simple representation. So k into 0 and 0 into k, these are simple representations. But for non-simple, example for non-simple representation, so your V is k to k. It is not simple. It has the non-trivial sub-representation. It has the non-trivial sub-representation V dash equal to 0 to k. So next local, possibly non-commutative. What is local? What is local? Yep. Possibly a ring is local if if its non-invertible elements form an ideal. A possibly non-commutative we are taking. Possibly non-commutative. A ring is local if it's non-invertible, if its non-invertible elements form an ideal. So today I would like to stop my lecture here. Tomorrow we will continue. So in this lecture we have discussed the basic things for cluster algebra and a representation of QS and cluster algebras with some examples. So tomorrow I will continue with the decomposition theorem and example and Cabril's theorem, representation finite and other things. Thank you.